Okay, now we are going to study the reflection and refraction, which is closely related with the transmission and reflection coefficients. But as you will see that we have two particular choices. It is called as a particular polarization mode. So if you have in general a wave is propagating to the incident, you can have an incidence plane, and the electric field has two components. One is parallel to the incidence and the other perpendicular to the incidence. And they are called as a different polarization modes. And basically, they have different reflection and refraction properties. So first, I'm going to draw the diagram of the perpendicular to the plane of incidence. Plane of incidence. Then I plot here, I will try to plot here, draw the parallel to the incidence. So perpendicular to the plane incidence means that your electric field, if you look at the plane, is perpendicular. So basically the situation is the following. You have incoming wave. The electric field is perpendicular to the plane of incidence. So this is the electric field, let's say inside the board, and let's say the B is in this way direction. So are they mutually orthogonal? Yes, they are mutually orthogonal. K, incident wave, incident E field, and incident B. Okay, so it's making an angle with the interface I. Then that will be refract. Let's say that is refract. Some angle R. We can calculate from the Snell's law. Direction is K prime. And after the refraction, E prime like that, and B prime is something like that. They are mutually orthogonal to each other. So it's an incident wave and it's reflected, and you have B and E. For the reflected one, we know that the angle doesn't change. And E is, let's say, inward. You can take the outward, no problem. It should be perpendicular to the plane of incidence. So the boundary condition handles everything. And we have B double prime. In general, what are the boundary conditions? This is the polarization perpendicular to the plane of incidence. I will work on with the other polarization mode because that is very interesting. Both polarization modes have different reflection and refraction, transmission and refraction coefficients. But generally, boundary conditions are the same. Geometry is different. So let us write the general boundary conditions. What are the general boundary conditions? Since at the interface there is no any free charge density and current density, perpendicular components of the electric displacement should be the same. So that could be written in the following. This is, let's say, for the incident wave. And let's say the medium is the same for the reflected wave. Maybe let me say 0 for all of them. So double prime reflects the reflection, and without unprime shows the incident. And for the transmitted wave, medium is different, has a dielectric constant epsilon 1, and the wave vector, electric field of the wave vector is E prime. At this time, we are evaluating all of them at z equal to 0. We will have 4 boundary conditions, and all of them will be evaluated at z equal to 0. So where is the z? This is the z. But here, I did not put the perpendicular components. How do I introduce the perpendicular component? These are just electric field vectors at the boundary. How do I introduce the perpendicular to the surface? What do I do? These are E fields, or multiplied by epsilon electric displacement. So you should take the dot product with n and equate to 0. Okay, in general, so forget about this. This is for simple for that. For different polarization, what I am going to draw again. So what does this formula tell us? Electric perpendicular components of the electric displacements should be the same. How do I know? I have the electric displacement, incident, reflected, refracted, and dot product with n takes the perpendicular component. Is this valid all the times? Yes. Why? Because I equate the exponential phases and find the Snell's law. Okay? I don't need to write the exponentials anymore. So quickly, let me try to write the others. So that is basically the following. D1 perpendicular, or D1 D in out dot n is equal to free interface charge density, that is 0, and this is that equation. What is the other equation for the perpendicular components? What perpendicular components should be continuous? B dot n. So you know that the B in, B out at the surface should be continuous. So I rewrite this formula for you again. So there was a B here. Look at here. This term was the B. I write this B in terms of E because this is useful. Okay? Now that will be the B, but let us look at one thing here. What is square root of mu epsilon over K magnitude from the dispersion relation? This. What is the square root of mu epsilon over K? Look at here. 1 over omega. 1 over omega is the same everywhere. Okay? So I'm not going to write that factor. That is the same. So for the B field at the interface, what I needed, K cross E. This is frequency, 1 over frequency. I know that the phases exponentials are the same. So I write the B's in terms of just K cross E. Okay, do you agree? Okay? So K cross E0 for the magnetic field instant, K double prime cross E0 double prime for the magnetic field for the reflection. For the refracted one, K prime cross E0 prime for the magnetic field for the refracted. So in order to obtain that the normal component, again I should take the dot product with the normal vector at the surface. That is the other boundary condition, this second one. This is the first, this is the second. And what else we know? Now let us move on to the tangential components. Tangential components of the electric fields should be continuous. How do we make the tangential component? If this is the n unit vector perpendicular to the interface, you should now take the cross product. And that is simple. E0 plus E0 double minus E0 prime. So this is again reflection, this is refraction. Take the cross product with n. That makes everything tangent component of the electric field. That is simple. And what is left? What is left? Tangential component of the H should be the current density. So H in, H out. In order to get the tangent component to the surface, take the cross product with perpendicular, and this should be the free surface current density, and that is 0. Now let us look at this. This is B. How to make the B as a H? Divide to the mu. So, okay. What was the square root of mu epsilon over K? Frequency, 1 over frequency, that is the same. So, okay. So, we don't need this term. But in order to make a H, divide to the mu. So you will divide this to the mu. And what is the magnitude of the K? We have the direction here. Magnitude of the K is square root of mu epsilon times frequency. Frequency is the same. But this term divided to the mu. Therefore, altogether that becomes to the what? Square root of mu epsilon from K divided by mu will make what? Square root of epsilon mu. Epsilon mu. So basically, frequency is the same. Divide to the mu. Make the magnetic field as a H. K double prime E0 double prime, and for the refracted 1 over mu prime K prime cross E0 prime cross and have to be 0. So this is K E0, that term. This ratio is frequency, that is the same everywhere, divided by mu for the region incident and for the region reflected. For the refracted region, mu is mu prime. So go one more step. K is equal to K times K unique vector or n unit vector, and K is equal to, as we said, that is equal to square root of mu epsilon frequency, and this k magnitude and mu will make a epsilon of mu. This is the general boundary conditions. So I will not write this in explicit form for the perpendicular to the plane of incidence. You can do this as an exercise, mainly homework. The result is in your book in Jackson. Instead, I will study that the other polarization mode, and I will write the boundary as a practical form for the other mode, because the other mode is an interesting consequence. Let us draw the diagram for the other mode. Mu epsilon, mu prime epsilon. Now we have what? Parallel to our polarization is parallel to the plane of incidence. So this is Z, let's say N again, and we have an incoming wave I. Then in that case, this should be the K again, and the electric field is parallel to the plane of incidence. Let's say from the orthogonality of 3 vectors, B is out. Okay, now this is one polarization mode, this is another polarization mode. In general, wave could be anything. You can decompose your field perpendicular to the and parallel to the plane of incidence. But the different polarization modes have different reflection and transmission forms, even if the boundary conditions are the same, because geometry is different. So this is the incident, and that is refracted R, and B prime, let's say, and E prime. This is I, let's say E double prime for the reflected. That is B, and K double prime for the reflected. So this is the other polarization mode. So I am going to apply the boundary conditions parallel to the polarization for set of equations. Let me start from that one, because that is more easy for me in the beginning. For the B, K cross E is B direction. B is what? Perpendicular to the plane of incidence. So you don't have any cosines and sines. B's are in, out, out, out. So at the surface, they are the same direction. So what can I write at this instead of that? What I told you that this is K magnitude is mu epsilon frequency divided by mu, that makes square root of epsilon over mu. And that should be the E0 plus E double divided by minus same thing here, and that will be the epsilon prime over mu prime E0 prime have to be equal to 0. So this is the boundary condition in the open form, that one. Why? K cross E0 is K magnitude, E0 magnitude sine 90 degrees. Okay? And it is all the time K cross A is the magnetic field direction. You don't need any projection. You don't have an angle. Okay? It is tangent to the interface. Okay? So this is K magnitude, E0 magnitude sine 90. This is K double prime magnitude, E0 double prime magnitude sine 90 degree, because the angle between them sine 90. So only you are dealing with E double prime and E prime. Is it okay? The direction is the same. The other term is dealing with the angles. For that one, we will have the angles. For this polarization mode, what is the E0 cross N? What is the E0 cross N? E0 is this, incoming, N is this. So what is the E0 cross N? Do you see or not? So I can carry that E0 here. That is N. And that was, which one is K? This was K. This is again E, let's say. This was I. Therefore, what is this angle? This is E0, this is E0 for this one. Yes. The full angle minus the subtraction will lead you cosine I. Good. So therefore, this cross product will be E0, let me write here, E0 open parenthesis, I need a cosine I. For the one reflected, what will be changed? I will be the same, but the direction is shifted. Okay? So N cross I and N cross I will be in opposite direction. Therefore, the sign will be the negative for the other one. The leftover term, so again, E0, if you say that N cross E is positive, N cross E double prime should be negative because the direction is changing. N cross E0 and N cross E double prime. Okay? The other should be the negative sign. So then the other term, for the refracted one, you will get E0 prime cosine R is equal to 0. So basically, you have what? Two equations, and if you know that the incident amplitude, two amplitudes, one for the reflected, one for the refracted. You can solve this easily. So I am not going to spend the time. The final formula, which I am going to write, but I will interested in what the formula is saying. So I am raising the general boundary conditions. If you do some algebra, you will find that from here, maybe I should tell you as a next homework, this one, using this as a homework, derive the following expression. E0 double prime over E0 is equal to mu over mu prime m prime square cosine I minus n prime square n square sine I mu over mu prime. I will study in the board, but it will take time, and it's a standard algebra. I don't want to spend the time for this derivation, but you can easily derive this. So I write for only reflected one. I can write for the refracted one also, but I don't want to do. So what I am going to tell you, maybe you will need, when you derive this, you will need the following. First, you will need the following things. If you look at the result, what you have, you have cosine R and sine I. So for cosine R, you will use that the Snell's law. You can express in terms of sine I. And you will use also sine I as a sine I square as a 1 over sine I square is equal to 1 minus cosine I square. So you can do this. So I don't want to spend on any time on this. The result is interesting. So this is the amplitude of the reflection to the incident. And this is for so your homework is the derivation of this. So just derive this. I'm not going to write that the ratio of the transmitted with respect to the incident, but instead of, I'll do as if studied for the other mode. So this is for if you study carefully for the other polarization mode perpendicular to the plane of incidence, you will find a perpendicular to the plane of incidence. This is parallel to the plane of incidence, and is it the same? So you can look at your book, or you can derive, but only one derivation enough. So you will find that one. And cosine I minus mu prime n prime square n square sine square I over n cosine I plus mu over mu prime n prime square minus n square sine square I. So I wrote the second one without deriving, just to see that they are different. The particular mode parallel to the plane of incidence is important because at particular angle, incident angle, which is called a Brewster angle, the reflection goes to 0. So I did not derive this one. I did not derive this one also, but you are going to derive the above as a homework. I write the equations. But for the above, there is a very interesting consequence. Generally, materials has the similar magnetic properties. Mu and mu prime are equal to each other. And at angle, which is called a Brewster angle, that is the inverse of tangent minus 1 n prime over n. This ratio goes to 0. What does it mean? So I can show this easily. You can show also. At a critical angle, which is called a Brewster angle, Brewster, for particular polarization mode, reflection goes to 0. Everything enters to the other part, other medium. This is very important for designing the polarized eyeglasses I will discuss. So you can very easily show that this is indeed 0. Mu and mu prime will be cancelled out. So instead of you can use that the Snell's law, sine I over sine cosine. So you can use that the Snell's law. So just a second. Sine I over sine R, that is n prime over n. So you can use the Snell's law, and you can easily show that E0 prime over E0 is equal to 0 at this certain angle. So the meaning of this is the following. If you have two particular modes in an unpolarized wave, you have a perpendicular component to the plane of incidence and parallel to the plane of incidence. So when this is propagating at Brewster angle, one component transmitted to the other medium, but the other component is reflected. Basically, your incoming unpolarized wave becomes as a what? Polarized. So basically, this angle for the air and sea is 56 degrees. So during the sunset, or when the angle reaches the Brewster angle, two different modes or polarizations enters to the reflect from the sea. But for the parallel to the plane of incidence, all waves do not reflect, enter the sea. Okay? The reflected one is the other mode, that mode, and that is fully polarized. Then you can use the eyeglasses to cut this polarization. So when the eyeglasses are designed, indirectly it is used the Brewster angle. Because during the reflection, one component vanishes. No reflection for the one component. The reflected one will be the purely polarized. Then you can use the polarization grease in the eyeglasses, and you can reduce the reflection to the zero. So scattering reflection to the zero. So that Brewster angle is very important. So as your homework, derive this one. You don't have to derive the other one. And when you derive this, you will use the Snell's law and show that also at this critical angle, when you substitute there, this ratio goes to the zero. So that is all for the chapter 7. So we reviewed the chapter 7, and we studied that the homogeneous wave equations for non-conducting medium, and we derived the Snell's law, and we look at the different polarization modes, and we write the boundary conditions, and we find that we write the boundary conditions for particular polarization mode and discuss about the Brewster angle. That's all for today, and next time I'm going to start chapter 8. That will be the first we will investigate the electromagnetic phase when interact with the conductor, and then we will study that the electromagnetic waves in the guide, which is called the waveguide. So that will be continued.